Hello, welcome to another week in astronomy. Not necessarily the biggest stories, but the things I found interesting. So first up, a white dwarf which appears to be accreting a giant Neptune-like planet. Something that I think is rather cool. Many stars end their life as these things called white dwarfs. The inert core of a star after it finishes fusion and loses its outer layers as a nebula, but still is hot because of the stored heat of all that's happened before. Of course, now we know that many other stars have planets around them. It'd be interesting to find out what happens to those planets when a star goes through this process of dying. And one of the things we're going to have to look for, if we're going to make sense of this, is what we can find around these remnants. So this is the first time astronomers have found evidence of a giant planet like this, which has survived around a white dwarf. A group of scientists led by Boris Ganzik of Warwick University have found this, and it's quite interesting. So what they did is they found this white dwarf system that they're intrigued by and had a closer look at it. Now, one of the key points that's very useful for astronomy is the idea that different chemicals emit different radiation. There's a lot of complexity to this, but the simple point is you can look at the light a star emits and say have a look at what wavelengths it's emitting at or how much it's emitting at different wavelengths. And from these plots, you can start to work out and identify the substances that would be causing that emission. So, for example, there are particular signatures to look for things like neutral hydrogen, or say in a star's atmosphere more important would be maybe searching for oxygen, or later perhaps or some heavier elements in the star's atmosphere would be useful to look for. But because we can look at the light a star emits and identify the subjects we're causing it, we can start to work out maybe what's going on in that stellar system. So I'll read through the paper's abstract to try and give a brief explanation of what they found and why it's interesting. They begin by saying, the detection of a dust disk around the white dwarf star G2938 and transits from debris orbiting the white dwarf WD1145 plus 017 confirm that the photospheric trace metals found in many white dwarfs arise from the accretion of tidally disrupted planetesimals. They cite articles on both the white dwarfs mentioned in the abstract here. The short of this is we see disks of dust around some white dwarfs which are from these rocky planetesimals, and they then set out a problem. They say, the composition of these planetesimals is similar to that of rocky bodies in the inner solar system. Gravitational scattering of planetesimals towards the white dwarf requires the presence of more massive bodies. Okay, this is fair. If you want to scatter something towards a white dwarf, you might expect a body further out to help with this. And if you recall the giant phase of a star and the expulsion of its outer layers, you should probably expect the planetesimals in these systems to be things from farther out, scattered in, rather than remaining close to the stars when they go massive, are supposed to swallow up quite a lot of stuff and then basically kaboom in various different ways. You probably want planetesimals scattered in. And they then set up the problem with this in the article. They say, yet no planet has so far been detected at a white dwarf. Until now. They don't say that last bit. But you can see what they're setting up. That's what they've found. They've found this large icy body orbiting their white dwarf. They get measurements for the composition of the orbit, finding signatures for oxygen, hydrogen and sulfur. And they say the composition of this disk is unlike all other known planetary debris around white dwarfs, but resembles predictions for the makeup of deeper atmospheric layers of icy giant planets. That's an interesting quote there, and there's actually a bit more maths behind that, but yes, the composition that they detect resembles that of an ice giant planet in a close orbit, so that matter from it is accreting onto this white dwarf. They also have a check on the mass loss rate for this accretion, so obviously if matter is accreting from the ice giant onto the white dwarf, there will be a loss of mass for the ice giant. And what they show is that the rate of that mass loss could fit with a close-in giant planet. Again, there's more maths to that point, but I think it allows you to get the idea of what they're trying to do. It's a very interesting thing that we've found, and let's be honest, more than just the science, it's just a cool idea. This giant icy planet with clouds of matter just being accreted off it onto this very tiny star in the middle. It's rather wonderful. One other interesting thing of note is a bit of stargazing that happened on Saturday, December the 7th, that is rather cool, although I was in a cloudy area, so bad luck, I can't see it anyway. If you were in the northern hemisphere at the time, you could look at the star called Algol. It's often known as the Demon Star, and it's a bright multiple star in the constellation of Perseus. What's interesting in this case is it's not just one star, it's actually a system of multiple stars, with two of those stars in the system being very close together, less than the distance between Earth and the Sun. What's fascinating is we see these two stars orbiting each other. At some points in their orbit, of course, one star will pass in front of the other. This means that the system gets referred to as an eclipse in binary, or more accurately, it means that that eclipse of the two stars causes a drop-off in brightness. And interestingly, because of the star's closeness and its brightness, this is actually something we can see as amateur astronomers on Earth. We can see the drop in brightness as one star passes in front of the other. Depending on location and weather, not all of this would be visible, or it might not have been at all. But if you could see it over quite a short period of time, you'd see Algol dim in brightness and then rise again over a very short time period of order hours. And it's fascinating to me that one of these very important concepts in observational astronomy, which would be the change in brightness of one object due to another passing in front of it, is something that's so readily visible from Earth. It's not just something that a few select scientists can see in a lab. It's actually, in quite a lot of cases, not just this, something that's very readily seen from Earth. So that's all the interesting things that I want to talk about this week. Goodbye.